Hi, welcome to Module 3 of Lecture 12. Now, in the previous module, we dealt with calculating eigenvalues, and saw that for a 2x2 matrix, the eigenvalues are pretty easy to calculate. For a 3x3, it becomes a little trickier because not only do you have to do the determinant, which isn't so bad, but you have to solve the resulting cubic equation, which you often can't do so conveniently. Now, in the book, we have a carefully constructed example allowing you to solve it, but here we just ended with a cubic equation instead. You can solve that. Anyway, so now we're going to do eigenvectors. Eigenvectors require you to first solve for eigenvalues before we can do anything else. So that's where we're going to start. Okay. So let's pick a 2x2 example first. Now, to make it a little easier, we're going to want to have this one actually work out correctly. So I'm going to make up one here. Hopefully it will work for whole numbers for the eigenvalues. And then we're not going to do a 3x3 example here. I'll just sketch out how you would do one. There's an example in the book if you're curious to see how to do it in practice. But honestly, most of the time when you have an eigenvector equation for a 3x3 matrix, you're going to want to use a computer just because you're not guaranteed in most cases to get whole numbers for your eigenvalues. And if you don't get whole numbers for eigenvalues, calculating eigenvectors can be even messier. So we're going to stick with this example for now. Okay, so first 2x2. Here's our A. It's going to be 2, 3, 2, 1. Now A minus lambda I, we're going to construct, is going to be 2 minus lambda, 3, 2, and 1 minus lambda. The determinant, which is going to equal to 0, is going to be 2 minus lambda, 1 minus lambda, minus 2 times 3 is 6. This is going to equal 2 plus lambda squared minus 3 lambda minus 6, or lambda squared minus 3 lambda plus 2 minus 6 minus 4, 0. And that implies lambda, we can factor that to get lambda minus 4, lambda plus 1. And I actually cheated a little bit and spent a couple seconds ahead of time to make sure that worked out this time, because we actually do need them. We don't need them to be whole numbers, but it makes life much easier. Okay. So we have two possible eigenvector values, 4 and -1. Now, okay, so that's the setup. For every eigenvalue, you're going to have an eigenvector associated with it. The eigenvector, recall, is the vector that makes this eigenvector equation true. And there'll be one equation that will be AV equals 4V, and a separate equation that is AV equals -1V. And we're going to solve each of those as examples to calculate eigenvectors for each one of these things. So there you go. Now how do you calculate eigenvectors? Now normally you might think, okay, we can multiply out A times V, and we know that these things represent equations. Right? These things represent equations, and we would have two equations and two unknowns. Where the two unknowns, well, V itself is a vector comprising 1 and 2 elements. We want to solve for both V1 and V2, and that would tell us what the eigenvector V is. Now that's fine and all, but note a couple of things. One, we actually have a linearly dependent set of columns and rows here. We don't actually have enough to solve for two unknowns. We don't have two unique equations. We actually only have one unique equation because these equations are linearly dependent. Right? That was the whole point. We could compute this thing because A minus lambda I was a singular matrix. We could not just go through and compute it to find two unique values. We actually only have one unique equation, and so we know is one unique equation can solve for one unique unknown. That leaves one unconstrained. Now that's not that bad though. Why? Look at the equation itself. There's the equation. Well, if it happened to be the case that 1, 0 were an eigenvector, well, so would 2, 0 be, and so would 3, 0 be, and so on. Why is that? Well, basically 1, 0 is half of 2, 0. If you multiply both sides by 2, all you're doing effectively is changing a vector of 1, 0 to 2, 0. 1, 0, and 2, 0 should both be eigenvectors. In other words, eigenvectors are not defined uniquely, they're defined only up to a single multiplicative constant. What that means is we can choose whatever we want for one of the components of the eigenvector v and do all the other components relative to that one component. In practice, what we're going to do is call the first one 1 because it's easier. That'll work most of the time. There'll be rare occasions when it won't work out because the first element can't be 1 for various reasons. It has to be 0. In those cases, set the second element to 1, right? But usually, as long as the first element is not forced to be 0 by the equations themselves, you can safely call the first element 1. Okay. So remember what this was on the screen here. We had eigenvalues of 4 and -1. I threw this again, unfortunately. So here's our A again. And the two eigenvalues were 4 and -1. So let's start by considering the 4. That equation was v equals 4v. We're going to call v the vector 1, c, where c is some constant. And 1 is just arbitrarily chosen because we can't define our eigenvectors up to more than a multiplicative constant. So we'll just call the first one 1 and do everything else relative to that one. And we'll see if that works. If it doesn't work, we'll call the second one 1 and try it again. Okay, so there we go. How do we do this? Well, now we actually have two of the same equations. We'll check to make sure that it works. That's true. On the left side, you have 2, 3, 2, 1 times 1c. That's going to be the first row times the first column is going to give you 2 plus 3c. And the second row is going to give you, times the first column is going to give you 2 plus c. Now on the right-hand side, you have 4 times v. 4 times v is going to be 4 times 4c. That gives us two equations and two unknowns. They're the same equation. How can you tell? Well, the first equation is 2 plus 3c equals 4, or 3c equals 2, or c equals 2/3. The second equation is 2 plus c equals 4c, or 3c equals 2, and again we have c equals 2/3. So we're just verifying here that we in fact only have one unique equation. Two equations give you the same thing. Okay, so we're done already. V, therefore, for this example, is 1 and 2/3. It also could be 3 and 2 if you want to multiply through by 3 to get you nice whole numbers. It doesn't matter. The point is that is your eigenvalue, your eigenvector rather. And you can go home and check to make sure, you can check at home to make sure that when you multiply a times that vector, you get back that vector times 4. There's one of them. Second one. Same thing now, but instead of 4, we're going to use the eigenvalue -1. We still have the same two equations up front over here, because that part hasn't changed. But now on the right, we have -1 and -c. Again, we have two equations. They're the same equation. We'll check that. 2 plus 3c equals -1. That implies 3c equals -3, or c equals -1. Second equation, 2 plus c equals -c. That implies 2 equals -2c, or c equals -1. So they both work the same. V now is going to be 1, -1. And that's already nice and whole, so we'll leave it as is. And there you go. There is two eigenvectors corresponding to two eigenvalues. And again, you can check to make sure that if you multiply a times this v right here, you get back that v times -1. That's it. So that's a 2x2 example. Now I'm not going to do a full 3x3 example because again, you're not going to be doing it often yourself by hand. And anyway, it's hard to find the example that works out with nice whole numbers. There's one in the book if you want to check it out. But how would you do it in general? Well, in general, you'd have your A. We can just make up numbers here. And over here, we have a V. What's going to be V? Well, again, we're going to treat the first as a 1, which will work usually, unless the first one is forced to be 0, in which case it won't work, and you can try the second one as 1. And the other two are just constants. That's going to equal lambda times this. When you multiply this out, this will give you 3 equations, but there'll be similar equations. Two of them will be the same. Or this is a little trickier because they won't be exactly the same. You might have one of the equations be a multiple of the other equations, but you're only going to have two unique equations from this to solve your two unknowns. You can multiply this out if you want to. So this would be 3 plus c plus 0 is going to equal lambda, the first equation. The second one is going to be second row times the vector is going to be 0 plus c plus 2d equals lambda c. And this is going to be 1 plus 0 equals lambda d. And there you go. There would be three equations in three unknowns. We're not going to actually solve this thing because we're not going to actually solve this thing because it's going to be real messy. But the point is, that's how you go about doing it. You just let c and d be the second and third elements. If that works, great. If it doesn't work, make a different one. That's it. That gives you the eigenvectors for any matrix. And again, in practice, for anything above a 2x2, you're probably going to end up using a computer of some form or other. And just ask it for the eigenvalues and eigenvectors. But the procedure is the same. That's how you go about doing that. And again, a simplified example is in the book. Okay. So that's it for this. In the next module, we're going to discuss a couple uses of eigenvalues and eigenvectors in a little more depth. Thank you very much.